So in this video we want to discuss what's called a standard basis for RM or m-dimensional space. So here's the basic idea. Let's say we're working in R2. That's a horrible R2. Let's suppose we're working in R2. So this is a two-dimensional space. And we know the identity matrix for two-dimensional space. It's the matrix 1, 0, 0, 1. And what we want to do is look at the column vectors for this matrix. So the column vectors are the vectors 1, 0, and 0, 1. And what we say for R2 is that these two column vectors form what is called the standard basis for R2 or two-dimensional space. And because this is the case, what we can do is any vector in R2, so pick a vector AB living in R2, AB can be easily written as a linear combination of the standard basis. So to get AB, we could write it as A times the basis vector 1, 0 plus B times the basis vector 0, 1. So any vector AB in R2 can be written as a linear combination. This is called a linear combination, where you're adding scalar multiples of vectors as a linear combination of the basis vectors for R2. And this idea extends into Rm, where M is any dimension space you want. So if we're working in R3, the identity matrix for R3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. And the standard basis for R3 would be the column vectors of the identity matrix for R3. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. And this extends into m-dimensional space in the way that you expect it to. And the reason these basis vectors are going to be important to us is because if we have a linear transformation T, we can actually come up with the transformation matrix for the linear transformation T by looking at how the transformation changes or transforms the standard basis. And we'll actually build, in the next video, we'll build the transformation matrix that goes with the given linear transformation by looking at how the transformation changes the standard basis for Rm, and then constructing a matrix from the transform basis vectors.